Bismillahirrahmanirrahim. Dear students, today we are going to discuss Bargellini reaction. Basically, it is used to convert a ketone into a carboxylic acid containing functionality by the use of chloroform in the presence of base. But this basic reaction has been widely used by the different scientists for the synthesis of new organic compounds which have wide applications in pharmaceutical industries, etc. And many heterocyclic compounds have also been synthesized through the use of this reaction. So we will discuss some things about this reaction today. The main points of today's lecture is the introduction to Bargellini reaction, some history of this reaction, and also introduction to some modifications made in this reaction. Then the discussion of reacting species including ketone, chloroform, and the nucleophilic reagents like phenols. The bases used in this reaction and the solvents employed for the progress of this reaction. Then we will have an overview for the complete mechanism of original reaction. Original reaction means the reaction given by the Bargellini scientist. And then we will also discuss the complete mechanism for the heterocyclic synthesis. More generally, this reaction Bargellini is related to the synthesis of heterocyclic compounds including piperidone or piperidinone or morphilinone. So this is the about today's discussion. Bargellini reaction was basically given by the scientist, Italian scientist Bargellini in 1906 first time. Actually, it is not the first time reaction because another scientist, Link, the German scientist, has introduced some things about this type of reaction, but he was unable to clarify the nature of the product, and so it was named that we get the derivatives of phenol. But in 1906 Bargellini first time worked on this reaction and clearly found the nature of the product. The reaction includes the phenol, chloroform and acetone to form carboxylic acid in the presence of sodium hydroxide. Sodium hydroxide is an activator, not a catalyst. Then most generally or the most important modified form of this reaction is to use this reaction to synthesize morpholinones or piperazinones from ketones using the starting material of beta amino alcohols or diamines. Here you can see the beta amino alcohol or diamine. The amino group attached with the carbon is an alpha carbon and the next carbon is beta carbon, and so the XH, that is X mean it can be oxygen or it can be nitrogen. If it is oxygen, then it is an alcohol, beta amino alcohol. If it is alcohol, then we say that the alcohol is given preference here, and the alpha carbon is that given which is attached with this OH group, and beta is that which is attached to amino group, and so overall compound is named as beta amino alcohol, or you can say beta hydroxy amine if you go with respect to amino group. And second, if this X is nitrogen, then we say it is a diamine, 1,2-diamine or vicinal diamine, which reacts with a ketone and chloroform in the presence of base like sodium hydroxide, and dichloromethane is a solvent. Benzyl triethylammonium chloride is acts as catalyst, and we get the product. And this product is, if X is oxygen, then it is known as morpholinones, and if X is nitrogen, then it is known as pyrazinones. Pyrazine actually is a six-membered ring in which two nitrogen are present at 1 and 4 position, then it is called pyrazine. But as you can see, here is ketonic functionality present in this ring, so it is named as pyrazinones. Likewise, if X is oxygen, then this six-membered ring having nitrogen and oxygen at 1 and 4 position, and you know oxygen, in that case, if oxygen and nitrogen both are present in the heterocyclic ring, then oxygen is given preference and it given number 1 position, and nitrogen will be the number 4 position. Then this part is called morpholine, but here due to presence of ketonic functionality, it is also named as morpholinones. In 1894, Link, the German scientist, was the first to work on this reaction, and he wrote the products as hydroxyphenyl, hydroxyisopropyl ketone, or hydroxyisobutyryl phenol. That is, he thought that the nature of product is either a ketone or a phenol, but no, he didn't make an idea for the formation of acid functionality in the product. Then 1906, Bargellini, which was famous for his work on Fischer esterification. Fischer esterification, you know, it is the simple esterification action. We generally make ester from acid and alcohol in the presence of an inorganic acid. That is, a carboxylic acid is reacted with an alcohol in the presence of an inorganic acid like concentrated H2SO4 as a catalyst. This simple reaction is named as Fischer esterification reaction. So Bargellini was interested in the synthesis of coumarins and also worked on this Fischer esterification. So this work on coumarin led him to introduce to work this reaction also, and this multi-component reaction between phenol, chloroform and acetone in the solution of sodium hydroxide. Multi-component reaction is because it is one-part synthesis. One-part synthesis means we use all these reactants in a single flask, and there is no need to separate the products at every step. That is, first we introduce phenol and chloroform and we get a nucleophile, then we enter acetone, ketone, and we get the epoxide, and then we enter phenol in the same flask and we get the R product. Bargellini named this product as alpha phenoxyisobutyric acid. Alpha phenoxy, you can see here the structure that the carboxylic acid functionality, the next carbon attached to this functionality is named as alpha. We know that alpha carbon is that carbon which is directly attached to an to a functional group, and the carbon of the functional group is not linked or is not said as alpha carbon. So here you can see the alpha phenoxy group, benzene and then oxygen is attached to this alpha carbon, so it is termed as alpha phenoxy. And isobutyric acid, the remaining carbon of the acids are 4 in an iso way. Iso mean there should be one methyl at the as a branch in the molecule, then it is named as isobutyric acid. Here is I can discuss, there is some confusion that sometimes we named like N-pentane, isopentane, and then new pentane. N-pentane means straight chain, isopentane means as branch is present at second carbon, so we get two methyl groups at the corner as a branch, so it is termed as iso. And then new isomer in which one single carbon is directly attached to 4 carbon. Here you can see also, if I consider the main chain of butyric acid of 4 carbon, then the phenoxy group is as a substituent, and the 2 methyl of the butyric acid are present at the corner, so it is termed as isobutyric acid. A branch inside the molecule at some other position, a 3 position, 4 position, then it is not termed as isomer, isopentane or isohexane or isoheptane, etc. Then the most importance of this reaction is that it is used in the organic synthesis of new drug candidates. Drug candidates, new molecules which can act as a drug in the different diseases, and it is important for the pharmaceutical industry. Because we have previous knowledge that the molecular structure has great effect on the bioactivity of the compound, so the position of the same species, same group inside the molecule can affect the bioactivity, or the change in nature of the atoms or groups are present in the molecule can change the bioactivity of a compound. So it has a great impact on the pharmaceutical industry regarding the new drug candidates. So a feature of this reaction is it is easy to perform. As we have discussed, it is one pot synthesis. We do not have to separate the product after each step and then set a new reaction for the next step. Simply we can perform this reaction in one part, and also the reagents used in this reaction are readily available in the market. Although this reaction has been modified by many scientists and several times to increase its efficiency and to increase the nature of the modified products, yet the importance of this original reaction is much in this field. Two the most famous reactions which are based on this original reaction of Bargellini are Josik-Reeve reaction and Corey-Link reaction. Here is some overview of Josik-Reeve reaction, which is also using phenol to convert it into a carboxylic acid, and the Corey-Link has the same pathway, the conversion of an alcohol into carboxylic acid. The difference of these two reactions with Bargellini is that the Bargellini used chloroform as a starting material, starting reagent in the presence of base, but here the Josik-Reeve used trichloromethylcarbinol as the starting material, and the remaining reagent are same, like sodium hydroxide is used, acetone as a ketone is used, and the yield obtained is 95% about. The second example of Josik-Reeve reaction you can see is also a trichloromethylcarbinol which is directly attached to benzene ring, and it is converted on reaction with sodium hydroxide, lithium borohydride as a reducing agent, isopropyl alcohol as a solvent with the temperature, and we get an alcohol. This alcohol is through after reduction. There is first the formation of carboxylic acid, and then it reduced into alcohol. The second, Coriolank reaction. The difference of Coriolank reaction and Josek-Reeves reaction is the starting material. Here you can see the Josek-Reeves reaction used trichloromethyl carbinol as the starting material for the reaction, but Coriolank they used a ketonic form of trichloromethyl, or you can say trichloromethyl ketone as a starting material, which is first converted into the trichloromethyl carbinol after a reduction process, and then the next use is the same as for the Josek-Reeves reaction. Here is some points which show the importance of this reaction in the field of organic synthesis. That is, synthetically this reaction is very attractive for the organic chemists. First is it involved different substitution reactions in one part process. As we have discussed that it used all the reagents in one part process and in one part synthesis. The different substitutions include intramolecular nucleophilic substitution for gin dichloroepoxide, inter or intramolecular nucleophilic substitution with followed by chloride elimination, and then nucleophilic acyl substitution. All these substitutions are taking place in one parts in the same vessel. We will discuss in detail about all of these processes on next slides. Second, variety of heteroatoms as nucleophiles can be used, and this will get a variety of number of products of alpha substituted carboxylic acids. Third is it is inexpensive because the reagents used are not too much costly, and also the solvents used are available. So we can say that this reaction is inexpensive or cost effective reaction. Fourth one is the tolerance of protic media offers operational simplicity relative to typical epoxide substitution reaction. As we know, the epoxide substitution reactions are much famous, and epoxide reaction, epoxide moiety is a reactive moiety which is used in different reactions as an intermediate or as a starting material also. But the pathway of this reaction is in such a way that the reagent, the intermediate epoxide, can tolerate the protic media also, and we get the product easily, and there is no side products or no difficulty in achieving the product. Last point, the gin dichloroepoxide intermediates which are formed in this reaction are inherently reactive due to ring strain of this epoxide, but we do not have to add any strong Lewis acid or Lowry Bronsted acids for the substitution to occur, because the reaction medium is moving in such a way that they easily interact with each other and form the product, and we do not have to add other reagents into the reaction medium. One of the reactants used in this reaction is nucleophilic species. In the original reaction, the nucleophile used was a phenol, but it acted as a nucleophile in the form of phenoxide, because we perform this reaction in the presence of a strong base, and this strong base converts this phenol into phenoxide, which acts as a nucleophile and perform the reaction. If we discuss the different nucleophiles which can be used for this reaction, include alcohols, amines, and thiols. The order of nucleophilicity for aliphatic or for aromatic system is similar, that thiols are more nucleophilic than amines, and which are more nucleophilic than alcohols. If we explain this order, then first you can see that the size of sulfur atom is greater, and which is about 105 picometer plus minus some, and in case of nitrogen the size is 71 picometer. In case of oxygen the size is 65. The size of oxygen is smallest among these two, then nitrogen and then sulfur. So greater the size of the atom, greater will be the distance of the valence shell lone pairs from the nucleus, and so there will be the least attraction of nucleus on these lone pairs. When the attraction of the nucleus is least, then it will possess more space, and they are able to interact with the other species more strongly. So sulfur, due to having large size, is more nucleophilic as compared to nitrogen, and which is more nucleophilic as compared to oxygen. In case of aromatic system, the nucleophilicity decreases up to some extent as compared to aliphatic system. This is because of the resonance in which the lone pairs are involved in resonance towards the benzene ring. So the nucleophilic character is little bit low as compared to that of aliphatic system. But in aromatic system, if you compare the nucleophilicity of all of these three, the order will be the same. Here you can see the structures of these alcohol species having OH group, and amine species having NH2 group, and thiol having SH group, or SH group is also called mercapto group. And the second reagent is ketone, the carbonyl compound in the form of ketone. The most generally used ketone by the different scientists include acetone. The mostly used ketone is acetone. Then cyclopentanone, cyclohexanone, or some other, but mostly these are used by the different scientists. The basic thing which is kept in mind while using a ketone for this reaction is the steric hindrance, because the reaction should take place easily. So methyl ketones are small ketones with low steric hindrance having high reactivity are preferable for this reaction. The ketones having bulky groups are less reactive for this reaction, and so they are not used for this reaction. Here is a question. Although aldehydes, we know aldehydes are more reactive as compared to that ketones, so but they are not used here. If we explain this thing, then 2 points can be considered in this context. One is the aldehydes are not compatible with this reaction due to competing aldol condensation reaction, that there are chances for happening a side reaction of aldol condensation, and in the presence of strong base. And second, the relatively slow rate of dichloroepoxide formation. Another point, this is one point. Second point which can be considered, that the epoxides having low molecular weights are generally non-polar, more volatile, and there are some matters of stability, and there are chances, if the epoxide is volatile, then there are chances for the escaping of the intermediate, and the formation of product will be too low, and there will be a great effect on the yield of the reaction. So generally aldehydes are not used, and ketones are used for this reaction. And in case of ketones, the process, the mechanism, the way of reaction is rapid, convenient, and also cost effective. The third reagent, or you can say the first foremost reagent, is this chloroform, which in first step interacts with the base to form a carbon ion, which initiates the reaction further. So the foremost, the basic reagent used by Bargellini scientist was chloroform for the happening of this Bargellini reaction. But later on there are many changes in the reagents used. So in addition to chloroform, bromoform, bromal, chloral, bromal, chloral, and carbon tetrachloride, carbon tetrabromide have also been used for the progress of this reaction. And you can see the structure of these compounds: chloroform, chloral, carbon tetrachloride, then bromoform, bromal, and then carbon tetrabromide. The chloral and bromal are mostly not used in this current form. They are used in hydrated form, and if they are hydrated, then this aldehydic functionality is converted into two hydroxy groups at this carbon, which is termed as hydrated chloral or hydrated bromal. The different bases used in the first step includes strong bases like sodium hydroxide, potassium hydroxide, or sodium trichloroacetate. But the most recent discovery in this regard is the use of a mixture of potassium fluoride and alumina. This was used because there were some substrates which were able to be hydrolyzed by these strong bases of hydroxides. So the base used instead of hydroxide was potassium fluoride on with the alumina. This made the reaction more favorable or more stable reagent was this in the case of hydrolysis. And the different solvents used for this reaction include dichloromethane, the more generally, and then tetrahydrofuran, and sometimes toluene have also been reported as a solvent for this reaction. Here the complete mechanism for the original reaction given by Bargellini, that is the conversion of a ketone into a carboxylic acid derivative. First, the base, strong base like hydroxide abstracts a proton from chloroform, as it is partial positively charged due to presence of 3 electronegative chlorides, and we get the carbon ion. That is, the carbon gets the negative charge. This carbon ion, acting as a nucleophile, attacks on the carbonyl carbon of the ketone, and the pi bond is broken, and we get O minus, that is alkoxide ion is produced. This alkoxide ion then moves through intramolecular cyclization, in which this O minus oxide ion acting as a nucleophile attacks on the carbon having 3 chlorine, and one of the chlorine is removed as a leaving group, and we get an epoxide. This epoxide on directly reaction with the nucleophile, and here the nucleophile attacks on that carbon which is not containing the 2 chloro groups. Always the nucleophilic attack is on that carbon which is not attached to 2 chloro groups, but is attached to some other substituents groups. So after this, after the attack of this nucleophile on this carbon, we get the breakage of this epoxide and the removal of chloride as a leaving group, and we get finally the formation of an acyl halide or carboxylic acid chloride. Then the hydroxide ion acting as a nucleophile again attacks on this carbonyl of this acyl halide, and the pi bond is broken, and this negative charge then moves back, and chloride is removed as a leaving group, and we get the carboxylic acid functionality in this reaction, which contains the nucleophilic phenoxy groups also. The second mechanism is also given for the formation of heterocyclic synthesis. This reaction is given also given because most generally the Bargellini reaction is considered as the formation of heterocyclic compounds like this. So the mechanism of this reaction is also given. First is the overall reaction is written in which di-amino group when X is nitrogen, or amino alcohol functionality when X is oxygen, interacts with ketone in the presence of sodium hydroxide and chloroform as reacting reagents, and DCM dichloromethane as a solvent, and benzyl triethyl ammonium chloride as a catalyst, and we get the cyclic 6-membered cyclic ring, heterocyclic ring, which is if it is X is oxygen, then it is known as marfolinone, and if X is nitrogen, then it is known as pyrizinone. The first and second step are just similar as we have discussed in the last slide, that base interacts with chloroform and we get a carbon ion. This carbon acting as a nucleophile, it acts on the ketone, and we get an alkoxide. This alkoxide cyclizes to form an epoxide. Then the nucleophilic amino group attacks on this. If both are X is nitrogen, then both are amino, then you know there is no difference which amino is interacting, but you can see in the most of the reactions are the products formed, the structure of the product shows that the most generally interaction is from this amino group, first amino group, which is present in the neighboring of two methyl groups. This amino group interacting as our nucleophile interacts on the with the epoxide. And if X is oxygen, that is we having amino group and then also hydroxy group, and then we know that the more nucleophilic character is for amino group as compared to hydroxy group. So in case of OH, oxygen is not acting as a nucleophile here, but amino acting as a nucleophile attacks on the epoxide. And in case of two amino groups, the most prominent reaction by this amino group, which is adjacent to two methyl groups, may be due to these electron donating groups, which makes this amino group as more nucleophilic, which acts on the epoxide. And then we get the this intermediate product of acyl halide as for the last step. But here additionally the other step which is different from the last step. In the last step, this acyl halide was converted into carboxylic acid by the reaction of hydroxide as a nucleophile, but here in this case this X group, which is a nucleophile, if it is oxygen then it has 2 lone pair, if it is nitrogen then it has 1 lone pair. This acting as a nucleophile attacks on this carbon of this carbonyl group of acyl halide, and the chloride as a good leaving group is removed, and we get the cyclic process, heterocyclic ring. The removing product is HCl here, and the formation of product is the heterocyclic compound. So this is all about of today's lecture, and in next lecture we shall briefly introduce this Bargellini reaction, and then we shall move towards the step-by-step discussion of this reaction, and then the finally synthetic applications of this reaction. And this is all about today, and thanks.